Hello everyone, September 11th. Alright, we have another easy question, which means we have to get into this. At least read through, right? Read through this, understand how this binary lifting is going. I don't expect myself to fully be able to copy this, but then once we know this, I want to solve this. We haven't solved this problem yet, right? I need to solve this problem. And yeah, it's long overdue. I don't think I can solve it today, but definitely get the mindset ready. We'll solve this week. Alright, let's just do this one first. Count the number of consistent strings. An array. Wait, hold on. Okay, what we're looking at? Allowed. Alright, we have something called allowed. Distinct characters and an array of string words. A string is consistent if all characters in the string appear in the string allowed. So we want to return the number of consistent strings in words. Characters in allowed are distinct, so I can put that as an array, and I just need to count how many times. Yeah, I'm just trying to solve it in the fastest way possible. I have an array, length 26, true or false. Okay, no, 1 or 0. And then I am going to go through the string and count how many times what would be the easiest way to do this? Bit. How about using bit masking? Because it's only 26, right? That is not a bad idea. That's not a bad idea at all. So allowed will be a number, a bit mask, and the words will be as well. And we just check if the two are exactly the same. Dude, that is a solution. That is the freaking solution. Alright, so int allowed bit allowed mask 0 for int I. Ooh, char c of allowed dot to char array. We can say allowed mask or equal to 1 left shift C minus A. Okay. Actually, I can do a private int get mask, get bit mask, given a string str Okay, and then we say int mask 0 for char c of str dot to char a mask all equal to 1 left shift c minus a. Now return mask. So we say int allowed mask equal to get bit mask allowed. Int res equal to 0 for string w of words. If get bit mask w is equal to allowed mask rest plus plus, and I'll return rest. (1684) use bitmask to check for existence of matching. Okay, let's see if this one's right. Oh, I'm surprised. I'm very, very surprised. Oh, it's not equal. If all characters in the string appear in the string or not. All right. That is, okay, that is not what I had expected. Because these are all allowed. Oh, then we just need to check something as not. Okay, so I will exclusive all the two. Yes, we exclusive all the two. And then exclusive all the two, and then the matching will be 0. The non-matching will have a 1, right? And if the two, oh, we OR the two. We OR them, and then if everything matches, if there is no match, there will be an extra set bit, right? And then we do exclusive all, then it will not be 0. Okay, so basically we say if this or this, right, and exclusive all allowed mask, then why don't you just exclusive all at the beginning? Well, because I cannot exclusive all at the beginning. If I exclusive all at the beginning, we cannot tell, right? So we all them, all the two, and we have extra bit. So yeah, so we say this if it's equal to 0. This is exclusive OR, right? Ooh, I see. I have to use this. Okay, that's not right. So I get bit mask, I got its bit mask. I OR this, right? And then an exclusive OR allowed mask. Unless we have, you know, that would be very, very strange. Yeah, have to. I think exclusive or has higher precedence. Right. First, if a string is consistent, its or with allowed shall be allowed. Right. Otherwise, there will be extra set bits. Then, if we exclusive or allowed, only the consistent string would yield 0. Oh, alright, that should be right. Unless I missed something. Oh, happy, didn't miss anything. Force, Boolean array, hash set, bin manipulation. Actually, it's not on. It's on times. Yeah, on times something. I got it wrong because this part takes time. Yeah, this one takes time. What did they do? Is consistent. Check each character in the word. Okay. Ah. All right. We consider that one done. Yeah, but I will do n times k. Where n is length of words and k is average length of each word in the words array. All right. Lowest common ancestor of a binary tree. How do we do this? So we basically run a kth ancestor, right? So we will create an ancestor matrix. Jesus. So what we do is we create an ancestor matrix. What does ancestor matrix do? So we also have a depth. So I think ancestor matrix, I actually don't know what ancestor matrix is. So depth is to record the depth of each node. Okay, so create ancestor matrix, I have depth node.val and require it to be unique. Yeah. So just to record each node's depth, right? And ancestor node.val parent.val. So I put parent in it. and then we do binary lifting. We say, because we'll add this, and then we have the depth. And we say y1 left shift I is smaller equal to depth. The ancestor node dot val, which is the current, dot append. So what I want is ancestor node, and then we have an array. It's 2 to the 0, 2 to the 1, 2 to the 2 to the 2, all of their ancestors, right? The first ancestor, the second ancestor, the fourth ancestor, the eighth ancestor. That is what we're doing here. So we're gonna append. We need to know it's basic binary, like double ancestor. So we'll find its can we set I equal to 1, right? So we find its ancestor first. This is its ancestor, right? So we go to its ancestor, ancestor. Its ancestor's ancestor. And because we do binary lifting, we just do this -1 and this -1. Because this goes like halfway up, and this goes the other halfway up. So we fill it up, we do this, blah, blah, blah. We complete the ancestor for the current node. And then we call this for the left, we'll call this for the right, we increment on the depth. Okay, I understand this part. Now we want to find a kth ancestor, so we need to decompose k, right? So we have index 0, result is the current node, and then we have kk. Kk is the one that changes. So basically we are breaking down k, this number, into 1 and 0s, right? So if the current is a 1, and we have the index, then we will set its, we'll move there, right? Because we do right shift 1, so we go right to left. So basically we say it's, whatever number, so it will be, the 2 to the first ancestor, right? And then 2 to the whatever ancestor, and 2 to the whatever ancestor. So we just go to them, right? We go to them because we basically saying to get to that ancestor, we need to first get to the 2 to the first ancestor, right? And then we need to know the 2 to the third or fourth ancestor. Yeah, I say if you want to find the seventh ancestor, right? So what you want to find the seventh ancestor, we first find its first ancestor, and then we find the second ancestor, and we find a fourth ancestor, right? So we find its first ancestor, and then the first ancestor's second ancestor, and then that one fourth ancestor. All of them put together is a seventh ancestor. So that's exactly what it's doing here. You have the index, so the current, whatever ancestor, and then we change and change. So this is the kth ancestor. Okay, so these two are good. Now what we need is to find this lowest common ancestor. So we have two nodes, right? We have two nodes. So we set them up. We create a matrix. We get value, so we want P to be the higher one, right? Because if P depth is more than Q, then we swap it. So basically P is on the parent side. P is on the parent side, Q is lower. So now we want to find the with reset QV, we want to find Q's ancestor, which sits on the same level as P. So we find this, and then we start from QV, we'll find the depth, right? The depth is the difference between QV and P. So now PV and QV are the same. So if they are the same, right? If they're the same, then really? We return tree node PV? I thought you need to return that node directly. Oh well, because here I'm only putting a number, so this is where we need to change. Well, that's fine. Yeah, we can change that. So yeah, if they're the same, that means the Q's ancestor, which is the same level, is the value the same? I used to do this. Otherwise, we have a level with a depth PV. Well, I mean, it's the same level, right? So we want to go up. So this level cannot be smaller than 0. And then we have ancestor, right? The two ancestors, right? We have the two ancestors. And basically we start from the top, right? We start from the top. If they're not the same, right? We start from the top. What do you mean by they start from the top? Now if they're the same, because at the top they'll always be the same, so we reduce the level, reduce the level, reduce the level until the level where they become different, right? Yeah, we just go from top down, 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 down. At a certain point, they are the same. No, they are different. So at this level, they're the same. And then the next level, because level minus equal 1, now they're different. So when they're different, I'll reset PV, QV to their ancestor. They reset into the ancestor. Right, and then we have wait, hold a second, I need to read this one more time. Level is depth PV. Okay, so but isn't PV and QV, their depth is the same, right? Yeah, the depth is the same. So this is the total depth, and then we'll find their ancestor, and it should be the root, and it should be the same, right? And then same, so until we have something that they just diverge, right? That they diverge. Now, this level is getting lower and lower. Yes, because initially it's this, and this, and this, and this, until eventually, because the level will get lower, and then at a certain point they become different, right? They become different, and then we reset that, and we'll get their new depth. Okay, we get the new depths, and the level will be the maximum of their depth minus 1. Oh, this part is a little bit cryptic for me at the moment. That just means the level is too low, right? The level is too low. So because if we do level, they are not the same, right? So we'll pick, yeah, so the current level, so we'll pick them, right? We'll pick them, and we will get to their depth. So there's a new depth, right? But we can do this new depth minus 1. Why we can do this minus 1? Because we will have to go from, because these two are different, right? So it's at least it's their parent. So the new level can be minus 1. Okay, yeah, if their parents are not the same, then we reset the height. Well, basically just reset PV and QV, and then we reset the level, and then we just do it again until we find it, right? Until we find it where is equal to 0, because we have the current one is the same, and then our level is equal to 0, so we don't go up anymore, and then our current is your, yep, that makes sense. Not able to do it on myself, not able to. Even if it asks me just to solve it directly, I doubt I can do that. Oh, can I? Oh, because it's lowest common ancestor. How do I solve it without going through this? I remember it's, is it the left, the right? Yeah, so the first node that has P, Q, or itself, right? The first node that has P, Q, or itself, and that's the ancestor. Yeah, if P exists, so we go down. If you're a P itself, you'll return that, right? And then the one will have, okay, yeah, the first one that collects all three, that is the ancestor. But this is the official way to do it because it can be faster. Yeah, this is O n. This is probably O log n. But anyway, the goal is to solve this one. Have edges and stuff. Minimum number of operations to make the weight of each edge on the path from AI to BI. In one operation, you can choose any edge of the tree and change its weight to any value. So for each query, find the minimal number of operations required to make the weight of every edge on the path equal. In one operation, you can choose any edge of the tree and change its weight. Query is independent, meaning that the tree returns to its initial state. The path is whatever it is, return answer I. So basically we have two nodes. All the nodes are unique, right? Yeah, all the nodes are unique 0 to 0. So we have two nodes, we have a path, right? And we want to know on this path what is the count, right? What is the count of of the value of the edge, right? And we want to maintain the one has the highest count, right? Two to six. All right, so now basically, well, what are we doing? We're saying we pick some node. Ha, I forgot how this one is solved. I vaguely remember. No, I don't vaguely remember anything. I remember the idea is very simple, and the difficult part is to implement the lowest common ancestor. But what is the idea? That simple idea that you were talking about. I don't remember. The hell? Okay, root the tree at any node. And then we BFS it, DFS it. Frequency. Oh, frequency. Frequency. On each path, I have the frequency. So I will know from node, any path from the root to any node, I have the frequency. Okay. Now I remember. Now you have the frequency, right? And then you have the frequency of this, frequency from root to this, frequency from root to this, to another one. Then what you need to find is these two nodes' lowest common ancestor. Then you will know the frequency in that path, because the frequency from this plus the frequency from this minus the frequency of this, right? Because I have the frequency of this, I have the frequency of this, and if we add them together, minus 2 times the frequency from the root to their common ancestor, then you have the frequency of this path. And then you basically find the highest frequency, and then we do the total length minus the highest frequency. Okay, let's see if that's the right. There we go, that is correct. And you'll find can we use Targen? Wait, Targen, we use Targen to find the breaking point, the disjoint. Oh, because the disjoint is the same. You want to find someone who find your ancestor that, yeah, Target might work. Well, we already invested in the other one. Let's just use the other one. All right, that's that. We are